So I hope everyone enjoyed their spring pause and is caught back up, and I hope your other classes also gave you some type of break and that you're ready to go again. And well, yeah, so probably they didn't. Sorry about that. But anyway, we'll keep going. We have like 7 weeks left or something like this, and then the semester is over, and then everyone gets a summer break, and maybe you'll have to log into slightly fewer Zoom sessions for a little while. Okay, so anyway, but we'll keep going. And so today we're going to start the second half of the class. So the second half of the class is really about fields and Galois theory and representation theory. And so we'll kick it off just by recalling some basics about fields. Someone remind me what is a field? I've been practicing my infinite stare, so I can do this for a while. Right, so I've got one answer. It's a commutative ring with multiplicative inverses. It's good. So it's a commutative ring such that non-zero elements are invertible. And so equivalently, it's a ring whose only prime ideals, or so whose only ideals are 0 and R. Well, if those are the only ideals, they're also the only prime ideals. If these are, yeah, well, anyway. Good. So there's a ring whose only ideals are 0 and R. Okay, so where do they come from? Well, here's so. And somehow in a field, sort of despite in some sense being like the most complicated object because it has the most that you work with an algebra because it has the most structure on it. Like field has more structure than a ring, which has more structure than a group, and sort of which has more structure than a monoid, which has more structure than a set. Somehow fields are the most familiar because it's what you work with when you start doing mathematics. Like the real numbers are a field. When you're doing calculus, like the algebraic object you're working with is a field. So somehow, and the extra structure makes them more familiar, not less familiar. So the classical examples that you start out with as a child are the rational numbers and the real numbers. Then you get a little bit older and you learn about the complex numbers, which are not so far from the real numbers. What are some other examples of fields? Oh, good. So good. Yeah. So then you start doing some number theory and learning some modular arithmetic, and at some point you discover that FP, which is just Z mod PZ, is a field. So the field of P elements. Great. What are some other examples? Good. So I see someone posted F sub P to the N. So turns out, and we'll talk about this more, but probably many of you have seen it to some extent or another, that for any prime power, there's a unique field up to isomorphism of order that prime power. We call it f sub p to the n. Sometimes we write q for p to the n. Someone wrote matrix groups. So matrix groups are not fields for two reasons. One, matrix groups are not commutative, and two, like if I look at like sort of the ring of all n by n matrices, so yeah, I should, when I did this if and only if, I should say commutative ring. So sorry about that. Can't have helped. But like if you look at sort of, if you look at the ring of n by n matrices over like the real numbers, for example, then it has zero divisors in it. It is possible to write down sort of non-commutative things, like non-commutative rings that sort of satisfy this other property of having all non-zero elements invertible. So for example, like the Hamiltonian quaternions give you an example of sort of a non-commutative version of a field. So such a thing is called a skew field, but we won't do anything with those right now. And these are all, can someone give me a more esoteric example than any of these things? Or like, doesn't have to be, I mean, you can construct an example in whatever sort of, using whatever tools you want, but sort of give me something that sort of maybe is a little less, has showed up a little less commonly in your life before now than these examples. Oh, good. So someone in the chat wrote the following. Let me sort of change a little bit what they wrote and fix the coefficient field. So we could look at like C parentheses T. So this is the field of rational functions. In one variable over the complex numbers. I put that in quotes because that's not really, that doesn't really make sense. Depending on how you make sense of it, it's not sort of completely obvious how to make sense of it. So, and what this field really is, it's the fraction field of the polynomial ring in one variable. So whenever you have a ring, you can sort of take the fraction field of that ring. Let's say, I mean, a ring with no zero, let's say a ring, an integral domain, just so we don't sort of run into any subtleties. So whenever an integral domain, you can take the fraction field of that integral domain, and that gives you, well, fraction field is a field. And so in what the elements look at, like they're just sort of, so the elements here are just sort of f of t over g of t for f and g polynomials. And so and this is, if you think back to calculus or algebra or whatever in your introductory math classes, I mean, this is what you called a rational function, and like you learned like integration formulas for rational functions and things like that. Or maybe if you're lucky, you didn't learn integration formulas for rational functions, and no one made you do that. But okay, and so you can think of this like, you can think of this as a function because you can plug in any value of t, that any value of t that's not sort of a zero of g. So like this makes sense for, like this is a function on subset of the complex numbers. And it's a little bit subtle to call this sort of, if you think of this whole set of one, so you think of all rational functions at the same time, then like there's no subset of the complex numbers where all of these sort of defined functions at once. So like making sense of these as being functions is like maybe like a little bit subtle, at least from a classical perspective. But sort of any one of them you can make sense of as a function on some subset of the complex numbers, and then, but you really sort of algebraically, like as a field, like the way you define it, you just sort of define it formally as the fraction field of this integral domain. So just like in the same way that Q is equal to the fraction field of Z. So you're sort of formally inverting the non-zero elements. Good, so and this is one construction you can use that can give you sort of lots of other fields. Like if I have an integral domain, I can take its fraction field, and that gives me a field. And so, like, I mean, I could also sort of look at like C, T1, T2, and I could look at rational functions in. Yeah, so now let me do F, T1, T2 to Tn. So this is just fraction. So F is now just some field. So my coefficients are just some arbitrary field, and I can take the fraction field of polynomials in sort of n variables. I mean, there's no reason I have to stop at n variables. I could take I could take countably many variables. I just define sort of the field of rational functions in countably many variables to be the fraction field of the polynomial ring in countably many variables. Countably many variables. I could do the same thing. I could do the same thing with. I mean, I could do the same thing. Sorry, with uncountably many variables. I mean, you can sort of you can form a polynomial ring with any index set, sort of, for labeling your variables, and so you could sort of make sort of an uncountable a polynomial ring on uncountably many variables, or sort of any cardinality of variables, and take its fraction field, and you get sort of a field of rational functions in sort of however many variables and whatever that means. But okay, and this is a field. I mean, well, let me just say something. And fields have an interesting structure that we will. So okay, we're going to explore lots of things, but let me just say something weird on the subject of this example. If I look at here's something weird. If I look at the rational number, so I take the rational numbers, and then I take sort of the field of rational functions in variables ti, where sort of I is running over S is an uncountable set. So I just sort of fix something of cardinality the same as like the power set of a countable set. Sorry, uncountable. Yeah, I mean, I meant when I said undercountable, I guess uncountable maybe just means not countable. So I mean sort of the next cardinal up. So like the cardinality of the real numbers, or the cardinality of the power set of the natural numbers. Okay. Okay, well, let me just take S to be specifically. So S is going to be the power set of n. So this means I have a field of rational functions in variables indexed by the power set of the natural numbers. And then I'm going to do something called taking the algebraic closure of this thing. And then as a field, this is going to be isomorphic to the complex numbers. Okay, so, well, that's some funny thing that's true just sort of from the abstract structure theory field that I probably used the axiom of choice at least twice, maybe 3 times in sort of saying this. But okay, and well, so that, and maybe the point of this would just, for a second, maybe it looked like I was doing something ridiculous by taking the fraction field and sort of, so this was the algebraic closure. We'll talk more about algebraic closure, and algebraic closure is going to be something that matters to us, so we'll talk more about that. So, and maybe it looked like ridiculous for a second that I was writing down an example like this, where I took a field of rational functions and uncountably many variables, but in fact, like, that's just another way, and this is another way to get the complex numbers, so it's not so ridiculous. Okay, so that's sort of one. Okay, that's some examples. I mean, here I'm taking very simple polynomial rings. I'm taking and polynomial rings are very simple. I'm taking these simple rings, I'm taking their fraction fields to get fields, but like I could take more complicated rings. So for example, I could take, let me look at CXY, and then mod out by the polynomial y squared minus x cubed plus 1. And then so this polynomial you can check is irreducible. Okay. So CXY is a unique factorization domain. It makes sense to talk about irreducible polynomials. They generate prime ideals. So y squared minus x cubed plus 1, that generates a prime ideal. So this is an integral domain. And so then the fraction field is ooh, did I do this right? Sorry, I wanted to get a punchline, but let me check my punchline. Okay, I'll get a good punchline still. So the fraction field, like this is a field. And well, it turns out this is isomorphic. And this comes from, I don't know if you've taken some complex analysis, like it's sort of maybe not a first undergraduate course, but sort of anything more advanced, you've probably seen elliptic functions. And if you haven't, that's fine, but what I'll say next doesn't matter. That sort of is deduced using that theory, but like just to understand the statement, you don't need this. So this is isomorphic to the field of meromorphic functions on the field of meromorphic functions on well, I take the complex numbers and I mod out by sort of the lattice generated by 1 and then a primitive third root of unity. Let me see. Okay. For example, so this is a compact, and so whether this is a compact, this, okay, obviously you don't need to know the theory of Riemann surfaces or sort of complex analytic manifolds for this class, but this is a compact complex manifold, and so like the theory of holomorphic functions and sort of meromorphic functions sort of generalizes to sort of this setting, and you can sort of say what it means to have a meromorphic function on here. Of course, like if I took meromorphic functions on the complex numbers, like that's sort of like, that includes the rational functions, but there also includes more than that. So it's sort of some sort of analytic generalization of taking rational functions is taking meromorphic functions. But like the field, like there is a field of like the set of all meromorphic functions on the complex numbers, on the complex plane, like that's a field. The set of all meromorphic functions on any sort of one-dimensional complex manifold is a field. And in this case, so here's some one-dimensional complex manifold. I mean, so it looks like sort of you took sort of a parallelogram of the complex numbers and you glued together the opposite sides. So this is a donut topologically, but it's sort of a donut where sort of you have some complex structure, some atlas of complex charts on it. And that field of meromorphic functions sort of turns out to be isomorphic to the fraction field of sort of this integral domain. Okay, and this is, so this object is called an elliptic curve, and it's something sort of, it's some very important basic object that has a lot of different perspectives on it in number theory and complex geometry. But okay, and so, okay, just to say, well, we started off, and we gave these, we got a few fields out right at the start, but like these are just sort of scratching at the surface of possibilities for fields. I mean, there are many fields because, and so why are there many fields that are interesting? And you can sort of generalize at least some of the constructions I did. I mean, just by saying if R is a ring, and sort of P is a prime ideal, then, well, R mod P is an integral domain, and that's what it means to be a prime ideal. It means the so the quotient ring is an integral domain. So you can take the fraction field of R mod P. Now this is a field. Okay, and like if P was maximal, so if P was maximal, then sort of, yeah, so let me add that. So if P is maximal, then sort of R mod P is already a field. So the definition of being a max, and so then taking the fraction field doesn't do anything, so it just gives you back what you started with. And this is the definition of being a maximal ideal, is that the quotient ring is a field. And so well, if you ever have an interesting commutative ring, then like attached to that interesting commutative ring are sort of all these interesting fields you get by just taking sort of the fraction field of R mod P. So I know you guys talked about the Nullstellensatz and sort of some basic algebraic geometry last semester, and maybe some of you have seen some sort of some algebraic geometry before. But in this observation, sort of at the heart of the study of algebraic geometry. So, in one way to think about algebraic geometry from a sort of slightly more modern perspective is that, like, the theory of algebraic geometry is sort of, it just says that every ring is a ring of functions. Like, so you can sort of, like what you do in algebraic geometry sort of from sort of one angle is you sort of take an arbitrary ring and then you sort of produce some topological space and sort of then give some way of thinking about the elements of your ring as being functions on that topological space. And so, I mean, this is what you do when you take like spec of a ring. So spec of a ring sort of is just the set of all prime ideals. You equip the set of prime ideals with this Zariski topology. And then sort of, if you have an element of your ring, you can think of it as sort of a function on this set because you can think of it as a function on this set because what is a function? Well, it's just like it takes in a point and it spits out a value in a field. Like that's sort of classically what we mean by function. The only issue is like usually when you think about what a function is, like sort of every point the function takes values in the same field. And sort of the only difference in algebraic geometry is you sort of let sort of your function take values in different fields depending on which point you're at. And so here sort of like, this is the field your function takes values in sort of at the point P in the prime spectrum of the ring. But and then like the Nullstellensatz is just the statement that for certain rings, I mean, you can sort of use maximal ideals instead. And that's when you do this, you're essentially getting, so you can to replace those maximal ideals just with a single field. And then and sort of a generalization of the Nullstellensatz is that, well, not generalization, but sort of a related result to Nullstellensatz that sort of applies more generally is just the idea that like, well, when you interpret sort of elements of your ring as functions on sort of the prime spectrum in this sense, then like the only function, like the only elements of the ring that give you sort of the zero function are nilpotent elements. Right? And this is, okay, I'm purposely saying this all out loud instead of writing it because I don't want you to feel like you have to learn this stuff or remember it if this like wasn't part of the perspective last time or it's not something you know, but, and like what I just said was just the statement that the intersection of all the prime ideals in a ring is the radical of the ring. So just reinterpreted geometrically. But so anyway, this was not meant to be something you need to sort of have ready and present. I just wanted to sort of justify the statement that like for any like sort of this way I'm using of making fields of taking sort of commutative rings and then sort of modding out by a prime ideal and then taking the fraction field, like this is sort of a natural construction from many perspectives. And like these fields you get, like not only are they like called they're fields, but they, like they're really fields that show up in doing mathematics. So I mean, in this class, and in this class, it's true that like, well, we're going to spend a lot of time thinking about the rational numbers and finite fields and sort of specific properties, like doing Galois theory over these over these specific fields. But don't let the things we talk about trap you into thinking these are the only fields that matter. Like certainly they're not, and sort of there are many other interesting fields. I mean, let me use, okay, I'll just do it anyway. Here's one more example. And as like, we gave you this ring theoretic way of producing new fields. I mean, there's sort of also an analytic way of producing new fields. It's sort of related to this ring theoretic way. So another example of a field is the p-adic numbers. And so this is, you complete Q for the p-adic topology. So what is that? Well, this is defined by the p-adic absolute value. And the same, so I'll say what that is in a second, but I mean, this is analogous to sort of, I mean, the real numbers, like how do you get the real numbers? Well, they're just, you've completed the rational numbers, like in a sense, like the topological sense of completion. So you sort of just take all convergent Cauchy sequences for the topology defined by sort of the classical Archimedean absolute value. And just the point is, I mean, well, that's one absolute value on the rational numbers, and you can sort of think about the properties an absolute value should satisfy. And the main thing is like it should satisfy like the triangle inequality, so that you can sort of define a metric using it, and you should get sort of good properties of that metric, and then you can sort of take a completion. Well, anyway, yeah. So, and the p-adic absolute value. So this is a way, and this is a way of measuring distance. I won't write it down because I guess if you've seen it, you know it, and if you haven't, it's a little bit far afield right now. So you measure distance by sort of how divisible you are by a prime number p. So for example, in the 2-adic absolute value, like 256 is very small because it's sort of 2 to the 8th, whereas sort of 1 over 27 is pretty big because sort of it's 3 to the minus 2, but it's not divisible by 2 at all. So and things are small when they're divisible by 2. And it turns out like this sort of defines like a good notion. Like if you sort of use this notion, you get sort of an absolute value, and it sort of defines all the good properties, and you can use it to define a metric, and you can complete the rational numbers with a metric, and you get sort of some new field called the p-adic numbers that sort of like basically you should think is just as good as the real numbers. It just sort of happens that we grew up in an Archimedean world instead of sort of a non-Archimedean world. And so so we're sort of familiar with the real numbers, even though sort of the p-adic numbers are sort of just as good. Well, anyway, so we're not going to do anything with the p-adic numbers, but I think these are important in number theory and geometry, and there's important in all sorts of areas. And I just want to sort of illustrate that like sort of the things I said here, and sort of I gave this very general construction for producing fields. Like even that, like sort of, I'm far from having illustrated like all of the useful ways there are to sort of produce sort of new fields starting from rings. I mean, this completion property is also very important. Like yeah. Oh, okay. So there are lots of fields. That's sort of the statement, and we're going to study field theory. So we're going to study some very specific aspects of fields. And the first thing I really want to go over is like why the rational numbers and the field with p elements, like why they're so important in field theory, like why sort of they were so quick to come to our heads when we thought about field theory. And so there's besides just our sort of lived experience, there's actually like a structural algebraic reason that these fields show up a lot. Okay, so observation. If K is a field, then there is a map there's a unique map from Z to K. So it sends 1 to 1, 2 goes to 1 plus 1, 3 goes to 1 plus 1, 1, and so on. So a map of this is, and there's nothing special about K being a field yet. I mean, this is true for any ring. Like any ring has a unique map of rings from the integers. because any map of rings has to send 1 to 1, it has to respect addition. So it has to send 2 to sort of whatever 1 plus 1 is, and so on. Okay, so good. Well, I have this map of rings, and sort of one of two things is going to happen here. So, well, this map has a kernel. And what are the possibilities for the kernel of this map? Yeah, good. So in the chat, someone just wrote there the 0 ideal or the ideal P generated by some prime number. Why? Well, so K is a field. So that means any subring of K. So the image, so let me give this map name. So the image of phi, which is isomorphic to Z mod the kernel of phi, is an integral domain. Well, why? And just because it's inside of K, like because it's inside of a field. And sort of in a field, there are no 0 divisors. So in particular, like if you have any subring of a field, any subring of a field has no 0 divisors. So it's an integral domain. So the subring of a field. Okay, so that means the kernel of phi is a prime ideal. And well, Z is a PID. So we know what the prime ideals are. So in every ideal is generated by sort of some element, and then the prime ones just correspond to the irreducible elements. So here, or to the irreducible elements in 0. So in here, P is irreducible, exactly. So the ideal generated by an element is irreducible exactly when that element is sort of a prime number. These are all of the prime ideals of Z. Okay, so that means is either, well, if the kernel of phi is 0, then you have an injection from Z into K. But then by definition of sort of fraction field, or the definition of localization, this extends to a map from Q to K. So this is sort of by definition of localization. By definition, or sort of the universal property of localization. So in the fraction field, so Q is the fraction field of Z. That just means you're localizing at the multiplicative set of all non-zero elements. And like to give a map from that localization to some other ring is just to sort of to give a map to that ring such that everything in that, every non-zero thing maps to something invertible. But of course, I mean, everything in the field is invertible. So this satisfies. So I mean, okay, and I could spell this out more, but this is obvious, sort of probably obvious to you anyway, even if you don't sort of have this sort of in your head as a universal property of localization. But it is a good exercise to go back and think about like what is the universal property of localization, and then sort of why is this statement just invoking that, and sort of maybe also. It won't come up so much, but I've found in past experience that people have often not carefully learned what the definition of the fraction field of a ring is, or like what the actual definition of localization is. And you can, and if you're sneaky, you can sort of get by with just the intuition if you sort of don't ever try to write down things carefully. And well, so if this, well, anyway, if you feel like this might be you, and maybe go back and just revisit the definition of localization and just think about it carefully. Okay, so good. So that's one possibility. So either kernel of phi is equal to 0, in which case you actually have an embedding of the rational numbers into K, or the kernel of phi is equal to P, in which case you have Z mod PZ, which is equal to FP. Embedding into K. Okay, so and it's sort of exactly one of these holds. These two cases. So I want so like either the kernel phi is 0 and the rational number is embedded into K, or the kernel phi is P for some just one prime number P. So it can't be, so this can't be true for both 2 and 3. Like I've either Z mod 2Z embeds in here or Z mod 3Z embeds in here. So here, and let me just say this definition / theorem that we've essentially sort of proved / like I said, we've essentially rationalized / proved is the characteristic of a field K is the smallest integer, as the smallest positive number, such that one plus one, so a positive number n, such that 1 plus 1 plus, if I add 1 to itself n times, what I get is 0 in K. So that's just another way of saying n is the generator of the kernel of this sort of unique map from Z to K. And this is sort of the pedestrian way of saying it. So that's the definition part, and then so the / theorem part is this, or sorry. So the characteristic, we say the characteristic is 0 if there is no such n. And so that means sort of the kernel of this map is trivial, and sort of you're in this other case. So so this is equivalent to saying, so a field K has characteristic P if FP embeds into K, and saying K has characteristic 0 is the same as saying Q embeds into K. Let me make a remark. So if R is any ring, and I guess for structure, let me write, and F is a field, then a map F to R of rings is injective. Then it's any map. So any map from a field is injective. So and here I could have just said FP maps to K, or the rational numbers map to K, and it would have automatically been injective. And the reason is because the kernel is an ideal and not equal to everything, because sort of a map of rings has to send 1 to 1. So I guess it's this definition again sort of depends. Probably this is not the first time I've been a little bit ambiguous. I mean, if you allow the 0 ring, then sort of this is not true for the 0 ring, but otherwise, this is true. So the kernel is an ideal not equal to F, which implies it's equal to just the 0 ideal, because the only ideals in a field are so the 0 ideal and the whole thing. So and this is a useful fact to remember. But here I just mentioned it because, again, sort of saying I have an injection from FP to K is the same as saying I have a map from FP to K. So saying I have a map from injection from Q to K is the same as saying I just have any map from Q to K. Let me make another sort of remark / like mini exercise. So if K has characteristic P, then sort of for any alpha and k, if I add it together p times, so alpha plus alpha plus alpha p times, this is equal to 0. So this is, and the point is, this is equal to p times alpha, by which I mean 1 plus 1 plus, okay, so I've just done the exercise for you. So the point is, this is just 1 plus 1 plus 1, so p times alpha, which is equal to 0 times alpha, is equal to 0. So in a field of characters of p, like you take any element and add together p times, you get 0. So somehow, and my way of thinking about this, all this is just like, in any field or any ring, like it makes sense to say p. P is an element of any ring because like 1 plus 1 plus 1 p times is an element of that ring. Like it's sort of the p in an arbitrary ring just means the image of p in the integers under sort of the unique map from the integers to that ring, which is just sort of 1 plus 1, sort of p times. And so saying a field has characteristic of 0 is literally this, or sorry, saying a field has characteristic p is the same as saying p is 0 in that ring. And oftentimes you'll find it phrased this way. And this is, I mean, a helpful way to think about it. And somehow, like, yeah. It's good to be careful about like sort of things like this and just make sure you, somehow, and you know, you probably, and probably many of you, again, sort of seen some point or another that sort of p is 0 in a rate, like, have seen some version of the statement, but it's good to sort of think very carefully about what the statement means, just to make sure sort of everything's sort of checked out in your head. Okay, anyway, good. So that's characteristic, and when the point here just was that one of the reasons sort of these fields FP and Q are so fundamental and important to understand is because like every field is gotten sort of from building on top of them. So if your field of characteristic P has a map from FP, so it's sort of in some sense you get sort of any field in characteristic P just by sort of adding enough things to FP. And you get sort of any field of characters of 0 by sort of adding enough things to the rational numbers. And like this aim, so turns out you can sort of make precise what it means to add enough things. And when I like said that you could sort of produce the complex numbers in this way, sort of taking sort of fraction field and sort of uncountably many variables over the rational numbers, and then sort of taking the algebraic closure of that. And what I was invoking was this idea that you can sort of build any field, any characteristic 0, sort of starting with Q and then sort of adding things in, and it's sort of invoking some more precise version of that sentence. Okay, so this motivates sort of the main perspective / structure we look at sort of relating different fields, which is that of a field extension. So, if K contained in L are both fields, we say, well, not surprisingly, we say K is a subfield of L. Or, and so more commonly, actually, we sort of think about it in this reverse perspective, because sort of this building up idea is so important. And we say L over K is an extension. And so extension, and really we should say of fields, but sometimes we just say an extension or a field extension. So this notation L over K for fields just means like K is a subfield of L, but somehow it puts the emphasis in a different spot. It says, like the idea here, like when you write it sort of K is contained in L, so somehow you might think you're starting with L and then like you're sort of cutting out K inside of it. Here you sort of write L over K to emphasize you're starting with some field K and then you're doing some procedure to build some field that's bigger. So it's just a notational and conceptual thing, but sort of it's a very useful it's very useful notation in the sense that sort of forces your brain to adopt like a perspective that is like more useful for a lot of problems in field theory. Okay, and so that's what a field extension is. And so the degree of a field extension L over K, well, we write it as brackets L colon K. So it looks like this is a similar notation to the index of a subgroup, and that's not a coincidence. So when we sort of talk about Galois theory, we'll see that the index, like this degree of extension sort of is identified with the index of some subgroup in a group in some settings. And so this is the dimension of L as a K vector space. So e.g., the degree of C of the complex number of the real numbers is equal to 2 because C has sort of basis 1 and I as an R vector space. So definitely like C is an extension of the real numbers. The real numbers are a subfield of the complex numbers, and in any complex number is just a real number times 1 plus a real number times I. It's the real and imaginary part. And so that's telling you that 1 and I are a basis for the complex numbers as a real vector space. And here, and the idea is the same. I mean, if you have a field extension, like, I mean, that means you have a map of rings from K to L. And so, well, L is a field, so you definitely can add things. So it's sort of, you have an addition, and then because K maps to L, you can sort of multiply things in L by elements of K. And so that gives you your sort of scalar multiplication, and like just sort of the associativity and distributivity laws for a field, for the field L, sort of tell you that this sort of is a structure of vector space. So, I mean, this is, again, sort of an important algebraic phenomenon, is that sometimes when you have more structure around, it's useful to forget some of this structure. Like, it's useful to forget some of the structure and then sort of ask what you're still left with, because that can sort of give you a way to sort of pick out useful pieces of information. So if we have a field extension, we can sort of forget some of that structure. We can sort of forget that L is a field and just remember that L is in particular a K vector space. And then we can take the dimension of that K vector space. And it turns out like this is sort of a useful piece of information you get that you sort of see once you forget a little bit of the structure. Often in mathematics, you're sort of piling on more and more structure to get sort of interesting information, but sometimes sort of you've piled on too much, and like you can sort of get a very useful invariant just by sort of forgetting a little bit. This is one of those cases. So, and just let me make a remark. I mean, and this can be infinite. And I mean, and for example, like when I take sort of the field of rational functions over the complex numbers, like that's an infinite, like that's sort of has infinite dimension as a K vector space. So, and so you may or may not have sort of thought about infinite dimensional vector spaces before. It's just depending on your background. But as the theory is exactly the same, you have to impose an axiom of choice to see that there's a basis. But if you have, we're going to have the axiom of choice, and so any K vector space has a basis, including infinite dimensional ones, and the cardinality of that basis is sort of independent of your choice of basis. And so because of that, like this dimension is, I mean, this dimension is a cardinality. So it can be infinite, and when it's infinite, like it's sort of, there are different types of infinity that it can be, like, because I mean, that's just what the dimension, like the dimension is just a cardinality of a basis. But we're not going to care about, for the most part. So for us, we'll just sort of write sort of n if it's finite. So n, some natural number n if it's a finite set. So if it's a finite dimensional vector space, so you have a finite basis, or infinity if it's not. So it turns out this notion of degree of a field extension, well, and I'm not going to say it's useless, because there actually are a couple of instances where it's extremely useful to still think about it, the specific cardinality. one example is you can give a very simple proof of the Nullstellensatz, like over, and you, well, anyway, you can give a very simple proof of the Nullstellensatz in certain settings using this, using sort of this distinction between different cardinalities, different infinite cardinalities, but we're not going to do that. And so for us, this notion of degree of an extension will be most useful in the case where it's finite. So that's how we'll treat it. Okay. So let's take, I guess we should take a break. We've had our spring pause, so now I feel like I've taken a 2-week break because the midterm was before it. So I almost forgot that we should still take a break in our class. So let's take a break, I guess, till 1:25, and then we'll come back and do just a little bit more about field extensions before next time. Yeah, we'll see you at 1:25. Okay, we'll get started again. So I'm going to return to this question of, we have a field extension L over K. In particular, K could be the rational numbers or FP, and sort of L could just be sort of an arbitrary field of characteristic or characteristic P. And then sort of the question is like how to build L from K. Okay, so here's in one way you can do it that reveals some interesting structure is to just try and add one element at a time. Okay, so and what I mean, suppose I have this field K, and then so suppose alpha is contained in L. I want to look at the field K parentheses alpha, which is sort of defined to be, so by this notation I mean the smallest subfield of L containing both K and alpha. So, and just, I mean, for this to be a definition, you have to check that sort of there is a small subfield satisfying this property. But I mean, this is just sort of, you can construct it just as sort of the intersection of all such. So if you just take the intersection of all subfields of L that contain both the field K and this element alpha, well, it's pretty easy to check that that's still a field. And somehow it's because, well, exercise check that's still a field, but it's pretty straightforward. And then, well, and the only issue is maybe this, and it could be sort of empty, but and it's not empty because there is, because all of them contain K, so sort of, well, K is not, so K is definitely in this, and then sort of this intersection, and the other thing to check is sort of the intersection is non-trivial somehow. So like you have to be taking an intersection over some actual set of things, but like L in particular is one such subfield. So really sort of, this is sort of not a degenerate thing. So this definition makes sense and constructs just by taking the intersection of all such. Okay, so we can look at this, and then what we're going to do actually is we're going to describe this field K sub alpha. And so, and the trick of everything and this is really somehow like just the basic trick that makes everything in field theory work, and sort of leads to everything else we do, is that sort of K parentheses alpha admits a simple sort of abstract description. So abstract, I mean as an extension of K, but not as a subfield of L. So I mean, somehow there's this distinction, like I have sort of K contained in K parentheses alpha is contained in L. And I could sort of try and describe this K parentheses alpha in two ways. I could sort of try and describe it just as a subfield of L. So I could try and say like how you cut it out as a subfield of L. Or I could say just like abstractly, like this is K is containing KL. So this is some field extension. And like, does this field extension sort of admit sort of some nice alternative description? And so this is sort of what we'll do. We'll see this sort of admits a nice alternative description. That's what lets us sort of think about this in a reasonable and pleasant way. And it's going to look very similar to something we just did. So, well, observation. So I have a map from K adjoin T. So let me take a polynomial ring in one variable. I'll call that variable T. So you could just easily call it X if you prefer. There's a map so from K adjoin T, the polynomial ring in one variable over K to L, sending sort of T to alpha and sort of equal to the identity map on K. So if I think of K as being a subfield of L, and I also sort of think of K as just being the constant polynomials inside of here, then sort of the induced map is just the identity on that. So this is, I mean, and this is just the universal property of polynomial rings. Polynomial rings are left adjoint to the forgetful functor. Anyway, and this is just the and this is the universal property of polynomial rings, but also like, and it's just sort of obvious from the definition, like the concrete construction of sort of the polynomial ring as well. Okay, so and there's a and really not just a map, there's a unique map for the polynomial rings satisfying this property. And so, well, what is the kernel of this map? And I said it like I was going to answer it, but that's actually a question for you. What is the kernel of this map? So I got that it's the minimal polynomial of alpha. Yeah. So, but what do we know about the minimal sort of? This is going to give you the definition of the minimal polynomial of alpha. So sort of what do we know sort of at one step up from that? Yeah, great. So it's irreducible. So the point is the kernel of this map is either, well, it could be zero, it could be the zero ideal, or it's, let me call it. This is a monic irreducible polynomial. So just like for when we have a map from the integers, we know what all the prime ideals are. Okay, so yeah, so step one, first, the kernel of this map is going to be a prime ideal because sort of it's a map to a field. A field is in particular an integral domain, and so sort of any subring of an integral domain is also an integral domain. So sort of K of T mod the kernel of this map is an integral domain. That means the kernel is a prime ideal. So the kernel is a prime ideal, but K brackets T is a principal ideal domain. We know the prime ideals are just the zero ideal and the ones generated by the irreducibles. The irreducibles in this case, and just like for the integers, we knew they were just all the prime numbers. Here we know the irreducibles, sort of, well, up to multiplying by a unit, the only irreducibles are sort of given by the monic irreducible polynomials. So in this multiplying by unit thing, like, it's just like in the integers, we sort of didn't think about p and minus p. So we only looked at the positive prime when we were sort of writing down all ideals. And here, like, to make sure we haven't written down the same ideal twice, we only look at monic irreducible polynomials. So this monic condition, this is just make sure you don't write down the same ideal twice. So there's a difference between the element and the ideal generated by that element, and that difference sort of is just given by, like, in two elements of your ring that differ by a unit generate the same ideal. But sort of the units in this polynomial ring are just sort of the units in K treated as constant functions. That means there's sort of a unique monic polynomial generating every irreducible ideal. So just sort of generating every prime ideal. It's just to recall what's going on there. Okay. So in this first case, if the kernel is 0, then this map from K of T, the polynomial ring, to L is an injection, and it extends uniquely to the fraction field. And for the exact same reason that when I had to map from Z to a field where the kernel was 0, like, it extended to the rational numbers. Here I have a map from K brackets T to L, and so, but it's injective, and L is a field, so this extends uniquely to the fraction field, which is just sort of the field of rational functions. So here's it. T maps to alpha. And in this case, we say alpha is transcendental over K. So in transcendental, like, what that means classically is it doesn't satisfy an algebraic equation. But what is the kernel of this map? Like, the kernel of this map is just sort of exactly like the algebraic equation satisfied by this element of L. So saying the kernel is 0, so saying sort of alpha doesn't satisfy a non-trivial algebraic relation, and so we call that transcendental. But so the ring theoretic way to think about being transcendental is sort of the natural map from the polynomial ring sort of extends uniquely to a map from the sort of field of rational functions. Okay. Otherwise, if the kernel is generated by sort of is one of these other prime ideals, well, it's generated by unique monic irreducible polynomial alpha T. We call this polynomial the minimal polynomial of alpha over K. And we get this map from K brackets T to mod M alpha of T. Now this injects into L. And this is an isomorphism onto its image. The image is, and it's sort of not so hard to check, so I'll sort of leave it as a thought exercise for yourself. The image is this K parentheses alpha. So the image of this map is the smallest subfield containing alpha. So we get sort of K, this map factors is an isomorphism to small subfield containing K and alpha inside of L. So I should have set up here, I mean, I said it out loud, but I didn't say it right in words. Let me write it in the transcendental case too. And this map factors as an isomorphism between sort of this fraction field. So, and this is sort of, this notation is bad, but it's just what it is. I mean, so this K here, this K parentheses T, that means the fraction, like the fraction field of K brackets T. So the field of rational functions in a single variable T. Here, this K parentheses alpha means the smallest subfield containing of K, or the solid subfield of L containing K and alpha. And when sort of alpha is transcendental, like sort of this notational ambiguity isn't so important. But here, sort of this sort of K parentheses alpha is not sort of the rational functions in the variable alpha. Like here, K parentheses alpha is sort of the small subfield generated by alpha. Okay. And in this case, it's sort of isomorphic to K brackets T mod MLT. So the point is, like, in this case, this is a maximal ideal. So you don't have to like take, like, this is a maximal ideal, so the quotient is a field. So that's sort of why you don't have to like then pass to the fraction field here to get something. Sort of already the quotient of is a field. And so this is sort of some algebraic description of this field, K parentheses alpha. Okay. I mean, so, and just to kind of, so minimal polynomial means sort of the smallest polynomial with coefficients of K such that sort of f of alpha is equal to 0. I mean, the reason sort of a minimal polynomial exists is precisely because sort of the polynomial ring is a principal ideal domain, and sort of like this set of all polynomials which vanish on alpha is an ideal. That ideal is precisely, sort of by definition, the kernel. And it's just saying the kernel of this map is just saying all of the polynomials that vanish on alpha. And so sort of taking a generator of that ideal is sort of just taking the minimal polynomial probably in sort of, maybe the definition you saw before didn't involve writing down this map, but like that's exactly what was going on. So it was just said in a different way. So that's how this all connects. Okay, great. So we'll do a quick example. So, well, if I look at, I have R contained in C, and I have the element I contained in C. So that's going to be my alpha. And I can look at sort of the smallest subfield generated, the smallest subfield C containing R and I. Well, I'm going to get a map now from R brackets T to I. And the kernel of this map, so this sends to here, sends T to I. And the kernel is the minimal polynomial of I. Well, it's easy to check. The kernel is just the ideal generated by T squared plus 1. I mean, this is definitely irreducible to the real numbers because it always takes positive values at a degree 2 polynomial. A degree 2 polynomial is over any field is reducible if and only if it has a root. So this is irreducible for R. So okay, so good. So I get sort of R brackets T mod T squared plus 1. It's isomorphic to the small subfield generated by I. But of course, I mean, I already know that C as a vector space is sort of spanned by, as a real vector space is spanned by I. So this small subfield is just the complex numbers itself. So I get a map sort of from R, I get an isomorphism from sort of this sort of abstractly constructed field, R brackets T mod T squared plus 1, to this sort of more concrete field sort of I already had sort of maybe from a more analytic perspective, the complex numbers. So quick question, how many, I mean, here I gave you one isomorphism between this abstract field and this sort of concrete field. Is that the only possible isomorphism? Let me say the only possible isomorphism that sort of is the identity on the real numbers. Yeah, great. So this is an important warning. Means sort of, you have to be careful about what problem we've just solved. So the problem we've just solved is sort of starting with sort of some element here, and then sort of giving like some element in the extension, then giving sort of some abstract description of the smallest subfield containing it. That's not the same as solving the problem of like sort of starting with a field that's described like this, and then sort of saying what are all the maps into the complex numbers from that field. So this is not the only isomorphism, because you can also send, so and what does it mean to give a map from R brackets T mod T squared plus 1 to, well, to any ring, but in particular the complex numbers? We have to say what it does on R, but we're sort of fixing that it sort of just should be the identity on the real numbers. So if it's the identity on the real numbers, then you just have to say where T goes. T has to go to some complex number, and that complex number has to be a root of T squared plus 1. And like as soon as you pick a root of T squared plus 1, you get a unique map sending T to that. So T go to a root of T squared plus 1. So these are and so you could take T, so the map sending T to I, this is what we just saw. But of course, there's another root to T squared plus 1 over the complex numbers. You could also send T to minus I. And so this map is, this is another map from this sort of more abstractly constructed field, sort of this concrete field, the complex numbers. And it's also an isomorphism. And well, but and then there's no contradiction or anything here. It's just sort of a warning to be careful about sort of just, you need to be, and when you're doing this, you need to be careful about sort of what perspective you're starting off, because both are going to be interesting. And we're going to use both. I mean, on the one hand, we're going to sort of often talk about sort of the field you get by sort of just taking the field generated by some element, but then we'll also often be talking about sort of the fields you sort of abstractly construct in this way. And then we'll want to sort of give relations between these two constructions. And the point is, like, if you start with a field that's abstractly constructed in this way and you want to sort of realize it concretely as sort of some subfield of something else, like that is not typically a unique choice. You have to sort of choose a root of the polynomial to send T to. And sort of that choice of a root can give you a different map, and like it can even give you different, I mean, here it gave you two different maps to the same subfield, but there are other situations where you'd get sort of two different maps that sort of had image two different subfields. So we'll talk more about this kind of thing. Yeah, so we'll talk more about this on Thursday. Okay, so but I'll stop here and I'll stick around for a few minutes if anyone has questions.